Okay, so let's get started with the session 6 of the electromagnetics and electromagnetics in the guided and wireless media course, which is basically offered on NPTEL portal. And the course instructor is Professor Pradeep Kumar from IIT Kanpur. I'm Shazam Bhatt, and I am a PG student at IIT Bombay and a DAD fellow at Institute for Solid State Physics at TU Berlin, and Paul Drury Institute for Solid State Electronics in Berlin. And I'm going to cover some of the basics and recap some of the concepts which have been covered in this course. And I should say what we are going to do is that we are going to cover some of the basic concepts which have been taught in the I should say, during this week in this particular course. So it will not be particularly possible to cover the entire things, but we are roughly going to cover basically what we are going to cover in this session will be particularly time domain analysis of the, uh, I should say, transmission lines. We're going to cover a little bit about Smith charts. Smith charts. We are going to cover briefly about some of the applications of the time domain analysis in, let's say, the circuits, particularly, let's say, the switch and maybe digital circuits, and how do these concepts, particularly the time domain concepts, manifest in the analysis of, I should say, the circuit related things wherein the switching happens. So mostly I won't be able to cover everything, so that's why I will stick to the basics and try to roughly summarize the things from my notes, which I am going to upload in the Google Drive, and you can go through them anytime. And what we are going to do is that we are going to cover these particular concepts. So let me just switch on to this particular mode so that there is no issue with the video. Okay, so let's first of all study about what has been covered during this particular week. Is related to the transmission lines particularly. Let me just switch on. Uh, So the transmission lines you have been talking about, let's say, you had for example, an intrinsic impedance of the transmission line, and then you have basically something related to the load end, which is, let's say, a complex load, something given by x plus jy, which is basically a complex load, and you have some sort of a microwave signal coming in, a voltage form, some, let's say, V plus and V minus, which can be which is going out. Similarly, you have currents I plus and I minus going in the both directions. Similarly, you have I plus and I minus going in the both directions. And you talked about those concepts. Now, what's going to happen? Let's say if you have a transmission line, something like this, and you want to compute the reflection coefficient at any point, let's say this particular point. Let's call this point as Z. Then that particular transmission coefficient will be basically given by the voltage going in this direction minus the voltage going in the opposite direction. So it'll be V minus divided by V plus, which will be the transmission coefficient. So how much is basically transmitted? So it's actually basically if you have something like, let's say, a box, then the transmission coefficient, if you have an incoming wave, which is basically incoming wave, then this is the transmitted wave and this is the reflected wave. So the transmission coefficient will be how much is transmitted. So how much is basically transmitted divided by the total incident wave. So how much is incident? That is basically the transmission coefficient. Similarly, the reflection coefficient will be, in this scenario, will be how much is reflected divided by how much is incident on it. And this is the scenario in all of the wave phenomena. Okay, I have talked about it in the first slide, first lecture itself. You can just refer to those slides. So when we input those particular values here, this is basically the wave going in the negative direction. This is the wave going in the positive direction, and you simplify it, you get gamma L e to the power j2 beta, which comes because of this summation. And you can write an expression at z equals to minus L basically, which will be gamma times L e to the power minus j2 beta L. So it will be some point L at z equals to minus L. This is the expression you get for the transmission coefficient. And now, for example, you have one important thing, that for a lossless line, the standing wave ratio is constant, and also the reflection coefficient is going to be constant. So it doesn't matter when there are no losses in the line. Okay. Now, for example, the important concept here is something related to how do you represent the imaginary numbers? You represent them in a complex plane. So when you represent them in a complex plane, so you have this as real axis, you have this as imaginary axis. Let's call it gamma I, let's call it gamma R. That means we now have reflection coefficient as a complex quantity. That means the reflection coefficient is going to have a real part and it's going to have an imaginary part. That is what we are going to represent on a complex plane. And when we have, let's say, for example, some number uh, of the reflection coefficient, it's going to, when we are going to compute its angle in radians, that will be, let's say, theta r, which will be the angle of reflection. Angle of reflection coefficient. This we denote as theta r, and let's say this is the magnitude of gamma L, because you know that we can represent any quantity as, let's say, magnitude of, let's say you can represent a complex quantity gamma as magnitude of gamma L e to the power j theta r minus 2 beta L. So that's what we basically represent in the complex plane. Now, now what is going to happen is that, for example, you can just understand it from the lectures itself, this part. But now, if we want to, let's say, compute the power, so this is really necessary, because you can get questions from on this particular concept, that how are you going to compute the power in this particular case. So power will be basically, the incident power will be the real part of the voltage going in this direction plus the current going in that particular direction, but the complex conjugate of it. Okay. Why the real quantity? Because that's what we exactly measure. You cannot measure imaginary quantities, cannot be measured experimentally. Okay, you only measure real quantities. Okay, it's the scenario everywhere. If you, let's say, have a power meter, what you are going to measure is basically the real power. You don't measure the imaginary power, which is basically the most of the time it represents the losses. And it's the case with everything. Let's say, for example, you have some certain real quantities. Even in all of the, for example, physics domain, you have certain quantities which are real, and certain quantities which are uh, certain complex quantities which are composed of real numbers plus imaginary numbers. So whenever you measure the things, you always measure the real quantity. This imaginary quantity is sometimes associated with the phase, sometimes associated with the loss. It depends upon what you are basically measuring. So that's why here we are basically concerned about the calculating the real component of it. When you simplify it, you get the power to be equivalent to the V plus magnitude square divided by 2 Z naught. Okay, this is the exact incident input power. What will be the reflected power? Reflected power will be V minus square divided by 2 Z naught, where this Z naught is basically the intrinsic impedance, which is, I should say, the transmission line impedance. Okay, this is the transmission line's own intrinsic impedance. And you see that this incident power is dependent on V plus and the reflected power is dependent on V minus. And that's as simple as that. Okay, now you can basically simplify this power, and you can write it in terms of something called as decibel, which is basically a tenth of a bell. Okay, it's just a unit. It's just a unit when you compare the two power quantities. You can write it in terms of a decibel. So for example, you're comparing P1 and P2 quantities, then you can write it in terms of log 10 P1 divided by P2. That is basically the comparison. But if you have decibel M, this is something called as decibel per milliwatt. That time you can write it as log 10 P divided by some 1 milliwatt, basically a reference power. It depends upon what you are measuring, whether you are measuring power, whether you are measuring any other quantity. This reference level basically varies. So you are measuring it most of the time with respect to 1 milliwatt. So this is basically a measurement with respect to 1 milliwatt. How much is it compared to 1 milliwatt? Okay, so that's why it's called as decibel per milliwatt. And and basically, it's sometimes it depends upon what sort of a reference value you use here. If you are measuring intensity, it is different. If you are measuring power, it's different. If you are measuring, let's say, pressure, it's going to be totally different value. Okay, now when you convert this into decibel losses, you're going to write it as 20 logarithmic of gamma L. Okay, where does this 20 come from? Basically, you get a V square value here, and the square will come before this, and 2 into 20, 10 will become 20, so this will become 20. So you have a you can find the reflection losses in decibels, which will be 20 log of. So reflection losses will be 20 log of 20 log of gamma. Okay. Now, for example, if the reflection loss is 0 dB, what is going to happen? You get that means the reflection losses is infinite. That means gamma L is equivalent to 0. That means you don't get any of the transmission. Okay. That means if you have, let's say, a box, if there is an incident wave and there is a reflected wave, there is no transmitted wave. Okay, that means all of the wave is basically going to get reflected. That's what basically is meant by this particular thing. Now, what can you use? Now, what can you do? Let's say, for example, if you have multiple transmission lines. Okay, so let's say, for example, you have multiple transmission lines, and you have, let's say, for example, transmission line 1 connected to transmission line 2 connected to transmission line 3. This is having length L1, L2, L3, so on and so forth. This is having intrinsic impedance Z1, which is the characteristic impedance. This is Z2, this is Z3, and this is connected to finally at a load ZL. So in that case, you need to find the Z equivalent. How are you going to find, and how are you going to relate? Let's say, for example, there will be reflection coefficient here, gamma L1. There will be here reflection coefficient, gamma L2. There will be overall impedance ZL1 seen from this end, and seen from this end it will be ZL2, so on and so forth. In that case, you have a very good tool which is basically called a Smith chart. Smith chart allows you to basically compute these resistances, basically impedances and reactances of such a network when you have, let's say, multiple of these transmission lines connected, because it becomes complicated to compute by hand. Now you have to compute at each of the junction. You have to compute it, then you have to compute at each of the junction. So Smith chart basically simplifies this particular concept. Nowadays, but you should also remember that these are now, I should say, not often used. You can basically write certain equations, and you can write a simple program or a code on a computer that's going to show you that what will be the lengths of these transmission lines, what will be the equivalent impedances of these transmission lines, because it has become easier because of the advent of the computers now. Okay, I'm not going into the details of the Smith chart here. We can maybe see in the end, because this topic it's a different topic altogether. And if you want to know more, you can refer to my one of my videos in on the YouTube in the playlist. You can check the playlist in my YouTube channel of microwave semiconductor devices, wherein I have basically covered that how you can use these Smith charts to basically evaluate certain microwave parameters, such as these reactances, resistances, impedances. Okay, so that's what I have basically covered in that particular thing. Now, but what is this? If we have to simplify, let's say, for example, we want to understand at any point of transmission line, how can you basically obtain the transmission coefficient, and how can you relate it to the impedance of the line? Okay, now you know that the transmission coefficient is the load impedance minus intrinsic the characteristic impedance of transmission line divided by load impedance plus Z naught. Okay, you can write these things as ZL bar minus 1 divided by ZL bar plus 1, where this ZL bar is something called as normalized impedance. And remember this thing that the Smith chart always gives you these normalized impedance values. Okay, this is sometimes most of the time you miss, but always you get this ZL bar, which is basically ZL divided by Z naught. So you have to normalize these particular values with respect to the uh, impedance of the transmission line. So whenever you get a question, just make sure that you are being asked whether you are asked ZL or whether you are asked ZL bar, because this is a normalized value, this is not a normalized value. Okay, so these are certain things you should always remember. And now, for example, when you talk about the this is basically quite complicated to show it on this particular board. I'll show you a Smith chart figure later on in one of the questions if the time permits us to solve those particular problems. Then we will basically refer to this particular Smith chart, wherein basically there are circles and arcs which basically refer to the which basically refer to the real resistances and impedances, and as well as you can find the transmission coefficient. Okay, and so what is basically in this image chart? First of all, you can see that there are the circular lines, wherein this is, let's say, the main circular part. Then you have basically these something like this is exactly not drawn to the scale. You have the unit circle and you have circle of zero point 0.5 radius. And then you have these arcs basically, which are blue colored. Okay, these are blue colored arcs. The essential thing is that these are circles of different radiuses. And these arcs, which are basically the part of a bigger circle, which you are not concerned about, they are used in some different field or there's a different concept altogether. So, for example, if you have a gamma L equals to 1, that represents the maximum radius of this particular circle. And each circle basically represents the constant gamma L value, or each circle represents the on each circle there is a it corresponds to the constant standing wave ratio circle. Okay, every external circle. Now there are other points. Let's say, for example, this point will refer to gamma L to be equivalent to 1, theta R to be equivalent to 0, because theta R is this particular angle. So this is theta R. And what is theta r? Theta r, I told you it's the angle. If you have, let's say, gamma I, this is gamma r. So the angle between them is basically theta r. Let's say you have gamma to be equivalent to x plus iota y. So what will be theta of this particular thing? It will be tan inverse of y over x. So that particular theta is basically represented here. Okay, so this represents the angle of this particular friction coefficient, angle of this gamma. Okay, now this particular point on the extreme end refers to gamma L equals to 1, because this is a magnitude, so it doesn't matter if it's, let's say, a -1 or +1. It's going to be negative on this particular end. And when you compute the angle for this, you get the angle to be 180 degrees as per this particular logic I showed you. Okay, so now, for example, you have certain more things wherein you can get the certain appropriate values of, let's say, uh, for example, if you want to understand, if you have a transmission line like this, wherein you have the load connected to it, and you want to understand basically if you connect a certain other network to it, let's say I call this as a network, which is basically a short or a shunt network, and you want to understand what should be the lengths of these particular shunts, or in the terminology they call it stub networks, so that you can basically minimize the reflection. So any of the incoming wave that wants to go to the load is basically will get reflected from this network. Okay, if this network was not here, let's say, so there was a reflection, some reflection of the wave, but you have connected this particular network at this particular point, And what has basically happened is now the instead of the wave taking the previous path, the wave is now going to go through this and is going to go through that, and it's going to minimize the reflection. So it's to minimize the reflections. Okay, that's what basically this short does, and it's called as stub networks. And often they are basically used to minimize these reflections. But what happens basically is that these shorts, or they are also sort of a lines, they also have certain basically intrinsic losses associated with them. And but they are very small losses, and they do not add a considerable amount of losses in the transmission line. But they are usually used to reduce these reflections in the transmission line. So all in all, what we have basically is that if we have, for example, let's consider this particular scenario wherein uh, you have a transmission line which is basically, let's say this transmission line is infinite. So it's as long as you can consider. So, and you feed in, let's say, for example, 10 watts of power to this transmission line. What's basically going to happen? The power is going to propagate, but with time, it's basically going to decay, something like this. And at the, let's say, after a few maybe kilometers of the transmission line, if you are going to measure power at this particular position, you are probably going to measure 0 watts, because this power will decay in a sort of a decaying sinusoidal fashion. So let's say if you fed it like a sine wave, then the sine wave will initially look like this, but as it will go through, it is going to get decayed like this. It will not be exactly like this, but it will decay with the, rather it should be, sine wave should look like this. It is going to decay with, so this is basically the Z, which is basically this direction, which is the length of this transmission line. So you see that there is an exponential decaying behavior of this particular uh, power which is being fed to the transmission line. And you can represent this as, let's say, for example, sine of omega t, sine of omega t, mm, into e to the power some minus alpha z, where this alpha z will be basically losses, and you get this exact particular curve of the losses through the transmission line. Now, in this case, what will be basically the reflection coefficient? The question is that. So the reflection coefficient will be actually zero, because the wave, the transmission line is infinite. So if z tends to infinity, the reflection coefficient is going to tend to zero. Why? Because it's not going to reach the end. And if it's not going to reach any end, it's not going to get reflected. It's as if these are transmission lines, and the wave is moving through it, but it's going to decay till infinity, and there is nothing to reflect these particular waves. So the reflection coefficient is going to tend to zero. It'll be zero for an infinite transmission line. Okay, but in reality, you know that we don't have infinite transmission lines. We have finite transmission lines that are basically ended with certain loads. So that's why when you feed it with certain power, some of the power is going to get reflected, because again we are considering waves. So when you are considering waves, you have the incident wave, you have the reflected wave, and you have the transmitted wave. That's as simple as that. And now, for example, if you consider, let's say, uh, this is the part which I was talking about, the impedance matching part, wherein if you can sometimes, let's say, for example, let me give you an example, basically, not in terms of transmission line theory, but maybe in terms of some physical theory which you can physically understand, or basically which you can feel, or which you can relate, basically something relatable theory about how these reflection losses or transmission losses takes place. So impedance matching is a certain, it's a technique that I talked about previously also. If you, let's say, for example, in the transmission line, you have a wave going in, and it faced certain impedance, let's say here, then you know there will be some reflection losses, and you know the reflection coefficient is ZL minus Z0 divided by ZL plus Z0. Z0 is basically the intrinsic impedance of the transmission line. Now, this is basically the reflection coefficient. You want to minimize it. And why you want to minimize it? Because you want all of the power to be fed to this particular load. And in order to do that, you have to make the load impedance to be exactly equivalent to the intrinsic impedance of the transmission line. As simple as that. And in the real life scenario, why does it basically matter? Because you might have seen that, let's say, for example, this is a patient. This is a body of a, let's say, a patient. Let me draw it. Not let me draw it. A funny body of a patient where this is the belly of the patient. These are the legs, and the patient is basically I should say on the bed. This is the bed. This is the patient, and you know that you might have heard about the ultrasound technique, which is basically something called a USG, ultrasonography, which is mostly done in the particular region, let's say a belly region or something. People want to image the inner organs and see what is their size, how are they behaving, whether they are enlarged, liver, kidneys, and all other things. So for that, what they do is that they bring in the probes, which are basically uh, they attach a ultrasonic transducer to this particular belly. Okay, so this transducer is basically this ultrasonic transducer. What does it do? It emits waves. But what sort of waves? It emits acoustic waves, sound waves. It emits sound waves in certain frequency. Let's say we don't care about the frequency. Let's say I'm giving a rough value of maybe 30 kilohertz, which we cannot hear. And what are those waves going to do? If this is, for example, a liver or a spleen or something, those waves hit the spleen and the liver, and they are collected back with this transducer itself. And using certain image processing techniques, though the images are basically generated, which is basically a complex phenomena altogether. And let's not go into that. But the essential thing here is, if let's say you remove this transducer here, and you consider the belly of this patient, you might have noticed that the USG is done before USG is done. What the technician does is that they apply a certain jelly-like substance on the belly. Okay, it's sort of a gel they apply before doing the USG. So the question is, why is that done? It is because if if this particular gel substance is not basically applied on the belly, the acoustic waves will get huge reflection from our skin because it's a totally different medium. Okay, so the acoustic waves will not basically penetrate through the skin. So they will have huge reflections. So the gamma R will be huge, the gamma will be huge. So there will be huge reflections of the acoustic waves. Why? Because of impedance mismatch. So because the acoustic waves are trying to, let's say for example, this is air and this is inside, this is the belly, this is basically the skin, and this is inside our body. So the acoustic waves are coming in, but they face a huge reflection from the belly because the impedances are not similar. Here the impedance was the rho 1 C1, here the impedance is rho 2 C2. So these are totally different numbers. This is basically the density into speed of sound, density into speed of sound. So when these two things do not match, the acoustic waves cannot get inside, and they need to get inside in order to map the body. So what they do, they play a trick. They just apply a certain gel here, which is basically certain special sort of a gel that has a similar sort of impedance as that of the skin, and a sort of a impedance which is in between the ear and the skin. So it has an impedance which is in between the ear and our skin or our body. So when that happens, the acoustic wave just penetrates, and some of the acoustic waves go through. There is always the reflection. There is always reflection part, but the some of the acoustic waves manage to now get through because the impedances have now lowered. We have lowered the impedances because of that gel, and then you get the reflected acoustic waves from the some of the organs, and they are mapped. So this is basically relatable theory that you can understand from the wave phenomena. And that is the similar thing what happens in electrical networks. If you don't match the electrical network's impedance with that of the load impedance, it's not going to feed the entire power to the load. So let's say this load is basically, so what I mean to say is that if there was certain incoming wave, it's going to face the reflections unless and until you don't match the impedance with this impedance, which is Z naught, which is basically the impedance of the uh, I should say line. So in this particular scenario, this line is basically acting like, let's say, air, and this particular load is acting like a, let's say, belly or stomach or something, skin, whatever you are trying to basically measure. So it is as simple as that, and you can just correlate these two things. They are not similar, but you can just understand the basically the similarity in these particular examples. So once the wave is coming from the air, it wants to go to the load, but it cannot go to the load because of huge impedances. It will get reflected and there will be huge losses. So for that, what you do is that you do something here. You do basically impedance matching. And impedance matching, what it does is that it feeds the maximum power to the load, okay, to the load. And that is why you have something called as maximum power transfer theorem. Those of you who have taken the network analysis courses in your undergraduate or in your first few semesters of undergraduate, they might have gone through this maximum power transfer theorem, where you have seen that the maximum power transmitted to the load ZL is only when ZL is equivalent to Z naught, when the impedances match, when the load impedance is exactly equal to the intrinsic impedance of the line. Therein you talk in terms of different, so you talk it in terms of circuits, but here we talk in terms of transmission lines, but the concept is basically similar. That is basically the concept of maximum power transfer theorem. Now, what are we going to do is that this is basically the idea of shunt stub matching, wherein which you can basically understand from some of the questions we can solve. But let's go to the time domain analysis first. So now, first of all, what is time domain analysis? So till now, what we have done is basically, let me just let me see if I can add one more page here. So what is let's say a time domain analysis? Time domain analysis refers to basically the, let's say you have a transmission line, and this is, let's say, the length of the transmission line. Let's say this is L and this is the Z direction, and you are feeding in some let's say this is the source resistance, and this is the source voltage. You're feeding in some wave or voltage. Now we are treating it as a wave, you know why. And because this dimension is of the order of wavelength, that's why. It's as simple as that. And what is basically happening is that you're launching certain wave with certain power, and you're feeding it to the load. Let's say this is a complex load. Complex means it has the imaginary part and the real part. So it can be written as some Z real plus J times Z imaginary. And you can also write it in terms of some e to the power j theta. Okay, with this theta angle can be tan inverse of Z imaginary divided by Z real. Okay, as simple as that, you know it. So now, till now, what we have been considering is we have been considering a sine wave with certain frequency omega, and we knew that this frequency, which is omega, which is equivalent to, this is the angular frequency. You can convert it into linear frequency as 2 pi times nu, where this nu is the linear frequency. And you can write the wavelength as speed of light divided by the frequency. And that is the wavelength. Basically, you compare this wavelength with the dimensions of the transmission line. Okay. Now, what we want to do in the time domain is that you want to analyze how long do these waves take to reach the load, and you want to know at what time they reach the load, at what time they get reflected, and at what time they get basically transmitted from this transmission line. So you want to understand those time scales. And why are these time scales necessary? Because they are going to govern the speed of the transmission line. How fast are these voltages slash currents being fed to the load. So that's the essential thing why you want to do the time domain analysis. Now, first and foremost thing is that the the important the important analysis that is basically necessary, why it is going to be necessary. Let's move on to this. It's necessary because of something called as signal integrity. What is that? I'm going to talk about it briefly in the upcoming slides. But the concept here is, let's say if we look at this figure carefully, this particular figure here, and what we are going to do is we have certain source voltage which is being fed. We have the source resistance, and we have the transmission line with intrinsic impedance Z0. The phase velocity is UP. This is the phase velocity, and this is the length of the transmission line. Let's forget about phase velocity for now. Let's not confuse you for the moment. Oh, it's not okay. So what is basically happening when the wave is launched? It will take certain time to reach at this particular point. Let's denote that as time delay TD. That means in going from this place to this place. Now, from this point, because of the load, because Z0 is not equal to ZL, so there'll be reflections. So wave will go back in this direction, and it will take time 2 TD, which is basically 2 times the time delay, 2 times TD it took initially. As simple as that. And now, whatever the wave you gave in here, let's say you gave a pulse here, something like this, a rising pulse. Let's say you gave a pulse like this at this particular end. At this end, you will receive a pulse with certain time delay, which is basically this time delay, TD. And when this pulse will reach back, you will get a pulse with time 2 TD. So this pulse will go back and forth, and you will have these sort of a pulsing phenomena inside this particular circuit. Now, why don't we see it? Because every time the pulse gets reflected, this amplitude is basically lowered because of the reflection. The entire reflection doesn't take place. Okay, so for example, you have this load and you have this pulse that went towards the load, and some of it got reflected and most of it got fed to the load. So most of the power was fed to the load. So the reflected pulse looks something like this now with the time delay of 2 TD. So the pulse when it reached here was something like this, a lower amplitude, but time delay of TD. This is 2 TD. Okay. Now again, what is going to happen is basically this sort of a pulsating effect is going to happen, and every time the reflection will occur, the basically this amplitude is going to get lower because most of the power is being fed to the load. Obviously, it depends upon how different are the load impedances and the intrinsic impedances, and it depends upon the gamma L, which is basically ZL minus Z0 divided by ZL plus Z0. If this gamma L is huge, if this gamma is huge, then there will be huge reflection. Okay, then you will see this amplitude going, I should say, it will be huge compared to the power being fed to the load. But this TD, which is the time delay, what does it depend upon? It depends upon the length of the transmission line divided by the velocity with which it is moving. Okay, so this is something called as propagation delay. Propagation delay. And now what is going to happen because of it? Let's say, for example, you have a circuit which looks something like this. You have a source voltage. Sorry, you have a source voltage, and you have a source resistance, and you have a load resistance. You know anything, let's say this is source, any voltage given to our two resistors in series is going to get distributed. And let's say, for example, if you compute the voltage across this resistor, which will be V1 plus, that will be the Z0 divided by Z0 plus Zs into the source voltage. This is basically the voltage being fed to the Z1. Okay, no, this is, let's say Z1, not this Z0. This is Z1. Okay, now what's going to happen? Let's call it ZL rather. This is ZL. So now what's going to happen at this will be at time t equals to 0. What is going to happen at time t equals to TD? Where this TD is basically L divided by U, and that means at time equivalent to the time delay associated with the I should say, for example, you launched a wave at time t equals to 0. It took TD time to reach the load. So now we are going to analyze after time TD what is going to happen. So what's going to happen is basically there will be some part of the wave which is going to get reflected. And how much of that is going to get reflected is basically given by this V2. That will depend upon the reflection coefficient times the earlier V1 plus, which is basically this. How much was earlier times the reflected. And this reflection coefficient, as I've been talking about, it depends upon the load impedance and the intrinsic impedance. Now, when the wave got reflected, it will reach back to this source end in time 2TD. Now, at time 2TD, what's going to happen? You will compute another part of a voltage, which is V3 plus. Now, that's going to depend upon the source impedance times the V2 minus, which is basically this voltage. Okay, so remember that if this is source, if this is source, this is load, it goes like this. So the pulse comes, it goes here in time TD, it goes back in time 2TD, and when it goes here, it is also facing the impedance because it's going back, so it's facing the source impedance. That source impedance has the reflection coefficient, which is gamma times S. Okay, that is the source impedance. Now this pulse will again go here, and it will again then go here, and it will keep on going. So it will go back, let's say, in this direction in time 3TD. It will go back towards the source in 4TD, then it will go again in 5TD, and this is going to happen, so on and so forth. But these effects we try to minimize in the circuits as low as possible. Otherwise, there will be, I should say, these are so detrimental for the circuits to work. That's why we try to minimize the reflection coefficients at this particular end. That's why the impedance matching is done. Otherwise, there will be these ringing effects, basically, these pulsating effects happening in the circuits. And how we do it and why we do it, that's what I'm going to talk about. So now, in order to understand this effect, that the wave is going here, some part is going here, then it's going back, this going back and forth, we have something called as space-time diagrams. It's a very fancy word, space-time, because we're talking about the waves. So when we talk about the waves, we have to talk about space and time, which is basically Z and T here. Z is basically the dimension, where a dimension in the direction of the length of the transmission line, and T is basically the time. And what we are going to now think about is, and you noticed one thing, that when we talk of a transmission line, we only talk of this dimension, Z. We never talked about the thickness of the transmission line. Think about it, whether it will have any sort of impact on the motion of the waves or not, because we are considering to be as perfect conductors. Okay, and uh, when they are perfect conductors, it's not going to matter if you, it's definitely going to matter beyond certain thickness, but we are considering most of the electromagnetic waves are propagating on the surface of these conductors because they do not penetrate the conductors. Okay, otherwise they will create a sort of a lag. So that's why we are considering them to be perfect conductors. This sort of analysis doesn't apply if you have maybe a certain sort of a line made up of semiconductors or insulators which are carrying the voltage. They do not carry as such because these are mostly metals. Whenever we use these sort of interconnects in the circuits, let's say this is one chip, this is another chip, these interconnects are basically traces. These are metals. These are most of the time, let's say gold. These can be maybe in certain cases, the metals are titanium, gold. In certain cases, these are titanium, gold, and nickel. These we use certain combinations, but these are metals, and they carry huge current on the surface of it because these electromagnetic waves cannot penetrate into the deeper regions of the metal because of the huge concentration of electrons. So that's the essential thing you need to have in mind. Okay, so now this particular phenomena, it has a very fancy name, which is that it is understood with the help of space-time diagrams or something called as lattice diagrams, wherein we basically denote the time in this direction, you denote the space in this direction, and what we do is that we consider this is not basically time, this is time over time delay. So this is a normalized time. It's a normalized time. And this is like 1, 2, 3. This means basically t equals to time delay. This is 2 time delay. This is 3 time delay, so on and so forth, up to 6 time delays. Okay. And now this is point z equals to 0. Basically, this is the source side and this is the load side. Okay. Now what's going to happen every time at, let's say, for example, this is t equals to 0 and z equals to 0. So you don't have any sort of a voltage when, so this is particularly this particular point. Let me show it here. Whenever, for example, you have, just like I showed you in this particular case, whenever you feed some voltage, after time td, what you are going to get? V2 minus, which will depend upon the load reflection coefficient times the V1 plus. And how much is V1 plus? This is V1 plus. So it always depends upon the previous values. Okay. So this was at time t equals to 0. This is at time t equals to td. This is at time t equals to 2td. So remember this thing. And you see that there is a pattern that at time t equals to 0, voltage V1 plus around this particular load was V1 plus. At time td, the voltage V2 minus is basically dependent on this V1 plus, which is this value. And at time 2d, the voltage V3 plus is dependent on this V2 minus, which is basically this V2 minus. So it's a recurring relation. It's a recurring relation which basically depends on each other. So unless and until you don't know the previous quantities, you are not going to compute this. You cannot, and if you don't know this, you cannot compute this particular value. So these are sort of a recurring values. Okay. So now, for example, you have uh, at time t equals to 0 and z equals to 0. And when you move to time td, after time td, the voltage is basically V1 plus, okay? And you face a reflection at z equals to L, and it goes towards the source end now, which is basically this end. It goes back to the source end, and now the voltage is V2 minus. At the source end, it again faces the reflection, and it goes towards the load end with the voltage V3 plus. Remember, when the voltage is going this direction, we represent it as V plus. When the voltage is going this direction, we represent it as V minus. So that's what plus and minus sign are representing. Okay, backward voltage minus, forward voltage plus. So now again at this load end, it's facing reflection. It's going V, and the voltage will be V4 minus, and it's going towards source. And upon subsequent reflections, basically the the voltage values are going to get I should say stabilized. Okay, so now what is basically how you can represent it in terms of a plot? Let's say, for example, you have if you want to basically see what will be the voltage at the load end or the source end rather. Let's say we talk about source end first. Initially at this is basically time axis. Initially at time t equals to 0, it had some voltage, which was a source voltage. After time 2d, it received some voltage. It can either increase or it can decrease depending upon what is the value of the voltage, whether it's plus, whether it's I should say if it is minus 1.1 volt or whether it's plus 2.2 volt, how much is basically the voltage. It can go on changing. It changes basically. Again, after time I should say 4 TD, it again changes. And but these changes are small, very small, depending upon the values, and finally it attains a certain value. But it's not going to it's not something like if the source voltage is, let's say, 6 volt, then there will be an increase in the source voltage to 8 volt. That's not what this diagram is basically saying. These values, these are not exact values. This is just to make you understand. It actually goes something like this. So if the source voltage was initially 6 volt, it will receive a back reflection and it will go like this, and it will, let's say, go to 5 volt, and it can go on increasing. It can go to 5.5 volt. It can then again reduce. It can go to again 5 volt, and it can then maybe increase a bit. It can go to something like 5.8 volt, and upon subsequent reflections the value is basically going to get stabilized in this particular network. That means the source voltage fluctuates up till certain time, which is the time given by this time delay. So it depends upon how many reflections take place, and most of the time up to 6 TD or 5 to 6 TD, I should say the voltage stabilize. Okay, and that is the same thing that happens from the load end. From the load end, the load voltage starts at time TD. Load voltage doesn't start at this point, because at time t equals to 0, you don't have any load voltage. The load starts to receive voltage after time delay TD, and it starts to increase. Now after time 3 TD, it again receives something, it starts to increase. After time 5 TD, it again receives something, it increases. After 7 TD, it again receives something and it goes on increasing, and finally it stabilizes. Okay? So that is the behavior of the voltages in these, I should say, transmission lines when the voltages are being fed. It's not something like we would have assumed that if we are giving a voltage of, let's say, we are giving a voltage pulse of 6 volt to a transmission line. This is, let's say, input, and this is the output, and we are expecting that we will get an output of 6 volt here. Okay, and let's say we were expecting that we will get output of 5 volt with 1 volt as loss, let's say. But that's not going to happen. What happens basically, if you give 6 volts, you get something like this value. It is delayed. It can be lower, but it fluctuates basically. And and those fluctuations, because of reflections, they make the source to even fluctuate, and that then it stabilizes. Okay, so that means whenever you have a circuit, you have a source. If it's open circuit, then the source voltage is going to remain at 6 volt. But when you close the circuit, when you close it and you end it with certain load, and if it's a transmission line, what's going to happen is the source voltage is also going to face certain fluctuations, and it's going to stabilize. And the load voltage is going to be delayed. It's going to have certain fluctuations, then it's going to stabilize. That is because of these reflections. That is why in when you when you use any of the microwave devices, what are microwave devices? These are the devices that basically process the microwaves, that basically process the microwave information. I should say, uh, transistors. Let's say, for example, certain transistors. Let's say something called as high electron mobility transistor, HEMT. It's a transistor that can process the microwave signals in around 50 gigahertz frequency, 100 gigahertz frequency. That's the max people have been able to show till now. It can process in, let's say, 4 gigahertz, 2.5 gigahertz, or even 5 gigahertz signal. But what is essential basically, whenever you have this sort of a device in a circuit, and this device is, let's say, for example, you have a HEMT structure, which is you have a HEMT device, which is a transistor, and you made an amplifier out of this. Amplifier means you are giving in some input signal and you expect the signal to be amplified. Okay, and this is mostly, let's say, used in radars. This is mostly maybe used in mobile phones, in the antennas, in the space communication. Okay, because they mostly use these microwave frequencies, or even the defense applications. What's going to happen is, if you have a if let's say you represent the transistor like this, let's say this is hemp transistor, and you are giving it certain sinusoidal signal to amplify, and you expect something like this, but that's not going to happen. What you are giving is fine, but what you are getting will be some sort of a distorted waveforms initially, and then you might get sort of a waves which we were expecting. And this is basically called as transient. It's transient means it's time varying totally. Not in sort of a time varying. It's not stable response, and this goes till up to certain time, which is basically dependent upon how fast the system tries to get to the stable value. Okay, and that is basically that happens with most of the devices. It's not only limited to transistors or devices. It even happens in the transmission lines in, let's say, for example, yeah, let me give you an example. For example, let's say, for example, you talk about digital circuits. Digital circuits. In a digital circuit, let's say if you have a transistor which is used for switching applications. Okay, switching applications means, let's say, for example, you have a NOT gate. This is a NOT gate, and you feed it 0, you get 1. You feed it 1, you get 0. Logic 0, basically. But the question is, what is inside this gate? It is basically a transistor, which is basically inside this gate. How these transistors are arranged, from your basic device physics course, or even if you don't know, these transistors, let's say if these are MOSFETs, which is metal oxide semiconductor field effect transistor, these look something like this. You have a substrate, let's say silicon, you have a source end, you have a drain, which is highly doped silicon, you have certain layer, which is a oxide layer, silicon dioxide or hafnium dioxide, and you have a metal. This is called as gate, this is called as source, this is called as drain. Okay, if you invert this particular device in the, let's say, negative 90-degree configuration, you you draw it something like this. Okay, so this is the gate, this is the drain. So let's say this is the drain, this is the source. So this is grounded. This is basically the MOSFET. Okay, and what's basically happening? And now there are two types of MOSFET. It is either N MOSFET and it's either P MOSFET. What's the difference? It depends upon what sort of carriers are basically being used in the channel to transmit. Let's say this is the channel. If the electrons are carrying the current, then it's NMOS. If the holes are carrying the current, then it's something called as PMOS. So you have two types of transistors. What you do is that you connect these two types of transistors together. You connect the PMOS here and you connect the NMOS here. So this is NMOS, this is PMOS. Okay, you connect, this is basically you flip it. This goes like this. The arrows basically show the direction of the current, and you connect the two gates together. So this is the common gate, and you ground this one. So this is basically the source. These are the drains. Okay, and what you now do, you connected the PMOS, you connected the CMOS. Sorry, you connected the PMOS, you connected the NMOS. Together they form something called as CMOS, which is a complementary metal oxide semiconductor. Why complementary? Because you have N, you have P. These are complements of each other. Okay. Now what happens basically if you give a what happened? if you give a 1 at this particular digit, if you give a voltage level of some voltage level, let's say 1 volt at this particular end, and if you compute the output around this particular value, you connect the output terminal here and you ground the other terminal, you compute the output voltage across this terminal, you will get a you will basically get a 0. So that is basically the NOT gate. So this is the inner part of the NOT gate. And it is sort of weird, but you need to understand how does the voltage and the currents behave in this particular circuit. Now, why it is essential for our example is because let's say let's say the question is that how does this transistor know whether this is 1 and this is 0. Basically the question is when we are talking about voltage, we are talking about certain voltage levels. We are talking about 1 volt, 2 volt, 3 volt, so on and so forth. Okay, and whenever you are giving voltage, let's say you are giving voltage something like this, and this is 1 volt, and you are feeding it to the transistor. Let's say this is the transistor now, and you expect it to you what do you expect is that you get some other voltage. Okay, but at the end of the day, these are only voltage levels, so these are continuous values, I should say analog values. Okay, and you in the output you also get these analog values even if it is a digital device. Now where does the question of digital come into picture? The answer is basically that there is nothing digital in real world. It's all analog basically. So basically it's all analog. The digital is just a myth. It's basically what happens that if you give in some voltage in the input, and if at your output, if your voltage level looks something like this, for example, if this voltage level, let's say V, if it is less than some threshold voltage, you consider that as 0. And if it's greater than some threshold voltage, you consider that as 1. That's as simple as that. Okay, and that gives basically rise to the concept of ones and zeros. Now, why is that important? That is important because if you have a circuit, if you have two circuits now, which are basically connected with the transmission line. So, for example, if this circuit, or not the circuit, if this is a transmission line and it's connecting to some circuit, to some circuit which is basically doing some digital calculations. Digital calculations. Okay, so what is basically happening is that whenever you are giving some, let's say you are giving some voltage level 1 volt here, or you are giving 1 volt, which is let's say logic 1, because it's above some voltage threshold, and when it goes to the circuit, because it's encountering this time delay, and then there is reflection, and because of that process, as we saw in the space-time diagram, that the output voltage basically rises like this and then it stabilizes. That means it slowly increases, then it slowly oscillates, and then it stabilizes. That is how the output voltage responds. So this output voltage is being fed to the circuit. Now, if this output voltage is being fed to the circuit, and if somehow the reflections from the circuit are huge, if the reflections are huge, this voltage will drop to like this value, and then it will increase and it will stabilize. And if this drop value is less than the threshold values of some voltage, what is going to happen is that earlier you send in 1 volt, which was treated as logic 1, and you expected that same logic 1 to appear at the circuit. But because of this reflection, the voltage dropped and it dropped below the threshold. Now it is being decoded as logic 0. So your circuit will basically receive logic 0. That means it will receive a bit 0, 0 bit. it was supposed to receive information as, let's say, you send continuous bits like this 1 1 0 0 1 0 0 1. So you send 1 1 0 0 1 0 1, but it is receiving 0 0 0 0 1 0 1. So basically the entire bit information has changed. So this information, let's say it represented maybe some sort of a important number or some sort of personal information, but now it's being decoded as 0 0 0 0 1 0 1, which gives a totally different notion. It doesn't represent the same thing. And why does it happen? Because of these particular reflections in the voltages. And these reflections in the voltage convert the digital information. They convert the basically 1 to 0 because the voltage fall below the threshold voltage level. And this is something called as error, bit error. So bit error means that the bit you have transmitted is not basically being decoded by the circuit because there is a bit error. Now what you can do, you can reduce this error because you can reduce the reflections, or you can do impedance matching. And but there's a trade-off. You will always have this time delay. So this time delay is basically another time delay that is responsible for the slow, I should say, uh, circuits or a slow working of the electronic circuits. This is basically the limitation of this electronic circuits. So that's why in the circuits we try to minimize the length of these transmission lines as small as possible because they create reflections. There's a problem that first they create reflections, second they create time delay, and third that results in the bit errors in the digital circuits particularly. Okay, and there is a concept basically when you go to digital circuit domain, there's a concept called as noise margin. Noise margin. Noise margin basically determines that how much noise is tolerable in the circuit, and tolerable means how much should this voltage level drop so that how much should this voltage level basically be so that it is readed as 1, and how much should it drop so that it's readed as 0. That's called as noise margin. That means if you have a output curve which looks something like this is the output voltage curve. If this is 1 volt and this is 0 volt, and let's say you determined let's say you are this is the, for example, threshold voltage. If you're if you received a voltage level of, let's say, these values, let's say you received a voltage of zero point 0.7 volt, zero point 0.6 volt, even 0.55 volt, everything that is above the threshold will be readed as 1. But when it goes below zero point 0.5 volt, everything here is readed as 0. So this will be bit 1, this will be bit 0. But if something happened that it brought the value below the threshold voltage, it's going to be decoded as 0. And what happens if some value is, let's say, exactly zero point 0.5? It's always treated as error. It doesn't basically, it's not exactly read. There are some techniques which are basically used, and we try to make this as sharp as possible, something like this. This should be as sharp as possible. Uh, and that is how basically the analog to digital information is converted. We want the certain voltage levels to be read as 1, certain voltage levels to be 0, but because of these impedances, there can be bit errors that can get incorporated inside the circuits. Okay, so now what? Now we can basically try to do what we can basically try to do is this is basically the part I was showing. From the space-time diagram, you get the output voltage, which basically starts at time delay TD. It increases up to certain value. Then after time 3 TD, it it receives another part of a wave, which can be negative, having negative voltage or a positive voltage, depending upon the reflection coefficient. Okay, I will show you in an example how the real values basically behave. And it can drop, then it can go on, it can increase, and then it stabilizes. And this is similar to some sort of a effect that you might have studied in your control system, something called as underdamped system. This is basically a stability criteria. That means whenever you are giving whenever, let's say you are giving, let's say this is input side, this is output side, whenever you are giving some voltage to the system, let's say this is your system, this box is your system. Whenever you are giving some input voltage to your system, the output voltage is delayed by certain time delay, and it increases slowly, and then it starts to oscillate, and then it stabilizes. That is basically the response. And this is basically the stable response. This is called as transient. Transient. And it goes up to, let's say, 5 TD or maybe up to 6 TD, depending upon how bad is the reflection, how good is the impedance matching. Okay, so accordingly, you might in control systems, whenever you study control systems, you study about underdamped systems, you study about overdamped systems. Okay, these determine how much damping of the oscillations take place because of the reflections, impedances, and all other things. That's as simple as that. Now, what else is there? I guess we covered this. Uh, this is covered. Is there anything else? Hmm, hmm, no, we have covered this thing. Yeah. Hmm. So another thing I wanted to mention here, basically, this is also essential because you should be at least tr knowing that what happens basically if you talk about let's say a transistor, because we are talking about we are the electronics, we are the electrical engineers, or we are electronics communication engineers. So whenever we talk about a transistor, you know that this is, let's say, for example, I will show a bigger picture. Let's say I'm showing a picture of a metal oxide semiconductor field effect transistor, field effect transistor, field effect transistor. So what basically happens, this is, let's say, a silicon substrate, uh, and basically what is done is that you have a silicon wafer, and you deposit certain metallic contacts over it, and or before that, you basically what you do is that you dope certain regions highly doped regions, and then you deposit the metallic regions over it, something like this. So you connect this terminal, this is called as gate, this is source, this is drain, and this is the top view of the silicon wafer. What you do, if you cut a cross section of it here, you just slice the cross section of this chip, and you look at the cross section from this end, front view. When you look at the front view, what you're going to see is basically this thing. This is basically the thickness of this silicon die, of this silicon wafer, and these will be the highly doped regions, which are basically under the metallic regions. So this is N plus region, this is N plus region. Let's say this is P silicon, P type silicon. And yeah, I forgot, before depositing the metal, here you also deposit the oxide layer. So you have an oxide layer here, you have certain oxides, and you have certain metals. You have a metallic layer. And this is connected, this is gate, these are the terminals, this is drain, this is source. So this is basically the front view of the transistor. That means if you basically draw it, it looks something like this. This is the wafer. This is the wafer. This is the thickness of the wafer. And if I draw it perfectly, this basically looks something like this is these are the highly doped regions. This is the metal. This is the metallic layer. These are the source. This is the source. These are metallic strips, by the way. This is a metallic strip. This is this part of same metallic strip because metal has certain thickness, and this is the oxide. So this is N plus source, this is N plus drain. So this is the metal also. So this is drain, this is gate, this is source, and this is P silicon. This is part of a wafer. It's exactly like this. So this is one of the transistors basically I'm showing. What happens basically is that you connect this source terminal, drain terminal, gate terminal. How you connect it is depends upon what sort of operation you want. Let's say you applied a positive voltage here, and you also applied positive voltage here, and you drained this terminal. That means you applied a negative voltage on this end. There's one more terminal, which is basically the bottom of this. It's called as body of a transistor. Most of the time, we also ground it and we tie these together. Most of the time, it doesn't happen often, but most of the time these are grounded. But uh, but let me not go into other details. But most of the time, let's say we ground it in order to simplify the system. Let's say right for now. So now what happens because of this positive charge, you have applied to the metal, you have applied to the metallic strip, which is gate. Because of the electrostatic forces, what it does is that it attracts the electrons below the oxide layer. So this is oxide. This one is oxide. So once the electrons get accumulated here, you have applied now a positive on this side and the negative on this side. So the positive is going to electrostatically bring the electrons towards this side, and the electrons are going to move in this direction. So you have the current in the opposite direction. So you have basically controlled the current flow. Now, if you remove this gate, the electrons will go and the current will stop, no matter how much voltage you apply here, at least ideally. Okay. What's basically happening? You know that this part of a transistor, which is something called as channel, most of the time it is modeled as a transmission line because you have these electrons flowing in it, and you have the source, you have the drain, and you're ready to go. So you have the source, you have the drain, you have these electrons moving in, and you can model this as a transmission line, something like resistance, inductance, and a capacitance. Resistance, inductance, and a capacitance, something like this. And you apply the same set of equations to this transistor also. This is the resistance in the now how do they come into picture? That's a different story altogether. Okay, for example, these capacitances, they come into picture because there is some charge storage at this position, at the below the oxide, let's say. And inductances are also associated with, although we do not mostly consider inductances, but these can also be considered. Mostly there are resistances, capacitances, but because of the motion of these electrons, there is also the current, the magnetic field associated with it. So this is exactly modeled as a transmission line. And if you have understood the transmission line approach here, you can understand the transistor quite clearly. Okay, because there are these currents and voltage basically that are flowing through the channel region. Okay, and and this approach is also essential if you want to analyze a microwave device. Microwave device is uh, is not it's not similar as that of a MOSFET because it has to handle a huge high frequency of the order of let's say gigahertz. Okay, and what determines whether a transistor can handle a gigahertz frequency or not is basically how fast an electron can go from this region to this region. And this, in the transistor terminology, this is something called as TA. This is called as transit time. And this transit time depends upon how long is this channel. It is the same thing that we study in transmission lines. That basically determines the how fast a transistor can work. You remember that if this is, let's say, source, this is drain, and this is the channel, and this is the length of transistor. So how fast an electron can go from this region to this region basically determines the transit time. And if you take 1 by transit time, that represents the frequency, basically the unity gain frequency. It basically represents how fast your transistors can work, whether they can work in gigahertz, megahertz, kilohertz, or yeah, this is the max they can go. Okay, and now what is basically essential is that somehow we try to minimize, somehow we try to reduce this length, minimize this time, and increase this frequency. So we try to reduce this. By reducing L, we reduce TA. By reducing TA, we increase the F. Why do we increase the F? Because we want them to be as fast as possible. We want them to process the signal as fast as possible. Okay, so that means if you have a signal like this, it can be processed by the transistor. But if you have a signal like this, it cannot be processed because the electrons cannot go from this end to this end very fast. Okay, for this signal to be processed, you require a very high frequency transistor, which is a special form of a transistor. Those are called as heterojunction bipolar transistors, high electron mobility transistors. These are basically microwave transistors. And the approach of understanding these particular transistors is similar. You use transmission line approach, you use microwave device approach. That is basically the same thing, what you use in electromagnetics. Why? Because because the high frequency, if you are feeding some high frequency to a transistor, let's say that high frequency is, let's say this high frequency is 3 gigahertz. Okay, and and you have a transistor with source, with drain, with certain channel length, which is L. So this is oxide, this is metal, this is oxide, this is metal. And what will be the when you convert the frequency to wavelength, it will be C over F. This will be 3 into 10 to the power 8. This will be 3 into 10 to the power 9. This will be around 10 to the power, let's say minus 1. So it's 10 to the power minus 1 meters. That is 0.1 meter. This is around, how much is 0.1 meter? This is around 10 centimeters. That means the wavelength of this particular frequency is basically 10 centimeters. Now, what is basically the length of your channel? The length of your channel is very small. It's of the order of micrometers. Even nowadays it's nanometers. That's basically called as channel length. So what basically happens is now it depends upon, because this frequency is determined how fast the electron can move from this end to this end. So if you want to process this very high information, high frequency, it should go as fast as possible. Okay, now for that you need to reduce this particular length scale. Okay, that is why there is uh, something called as technology node. Technology node. Technology node means you might have heard about nowadays the companies, they just advertise about the technologies used in, let's say, mobile phones. They call that it's a 25 20 it's a 22 nanometer technology, it's a 14 nanometer technology, it's a 7 nanometer technology, 5 nanometer technology. What are they doing? What are they reducing basically? Actually, they should be reducing this. They want to reduce basically this distance. If this is reduced, let's say if this is reduced to this distance, now the electrons can go fast and it can handle very super high frequency. Okay, it can process the information very fast. That means if the electron can go super fast from this end to this end, you can handle, let's say, 5 gigahertz. What does 5 gigahertz means? It is 5 into 10 to the power 9 billion cycles per second. That means your transistor can handle 5 billion processes per second, 5 billion, I should say, calculations per second. And if you want to increase the number of calculations a transistor can perform, you need to reduce this particular distance, or you need to make sure the electron goes as fast as possible to the drain end. That is basically the concept, which is understood also in terms of transmission line approach. And even your diode, which is basically a PN diode, let's say this is PN, these are the immobile ions. Even this diode is basically understood using transmission line approach. Obviously under certain conditions, not always, but under certain conditions, because there are resistances, inductances and capacitances always associated with this PN diode because of the charges. Okay, so now I think we went into a deeper part of it, but that's about this. Now what we are going to basically do, uh, mm, the I should say the question set for this particular session looks pretty much this looks pretty much easy, and you may be requiring some sort of a analysis to solve. Let's say we will solve some of these questions. Others, maybe I can upload it on the Google Drive because I have another meeting in, let's say, 15 minutes. I have, I guess, 20 minutes. I have another meeting. So we'll try to solve these questions as quickly as possible because they are very, I should say, simple problems. The first one, let's say it's saying that you have a 50 ohm lossless transmission line. So this is the intrinsic impedance. This is Z naught. That is given. This is you have a transmission line. The Z naught is 50 ohm, and you have the load impedance, which is a complex impedance of 45 minus 65 j omega. And incident power is given as 120 milliwatts. And what you need to find is the power dissipated by the load. So how much is the power dissipated by the load? So how much will be the power dissipated by this particular load? So for that, first you need to understand how much of the power reached the load and how much of it is reflected. So for that reflection, you need to first find the reflection coefficient, which is ZL minus Z naught divided by ZL plus Z naught. Okay, that means it is 45 minus 65J minus 50 divided by 45 minus 65 J plus 50. You solve it. How do you solve it? Uh, this will be minus 5 minus 65J. This will be 95 minus 65J. You basically rationalize it. 95 plus 65J, 95 plus 65J. You solve it, you basically get 0.28 minus 0.49J. You have to just multiply these two terms. You get the reflection coefficient, which is complex. So this is the real part of reflection coefficient. This is the imaginary part of reflection coefficient. And you can show these basically real part and imaginary part of reflection coefficient on the Smith chart, which I was talking about. You can show it there because this is the, let's say, imaginary part, this is the real part, and you have certain angle, which is theta. That theta will be tan inverse of minus 0.49 divided by 0.28. This theta will represent the angle in the Smith chart. Okay, now so what is now you need to find the magnitude. The magnitude of reflection coefficient will be under root of 0.28 square plus 0.49 square. So this will be 0.5664 approximate, which will be the magnitude. And now you have the transmitted power divided by incident power to be equivalent to 1 minus reflection coefficient square. And you can write the transmitted power as incident power 1 minus reflection coefficient square. And how much is incident power? It's 120 milliwatts. 1 minus 0.56 square. You get the transmitted power to be around 81.5 milliwatts. That's as simple as that. That's what the essential quantity here is, this reflection coefficient. It will be the essential in most of the questions you are going to get in these particular sessions. So this is the actual answer of this question. That is the transmitted power. And that is basically the power dissipated by the load. So you see how much is the loss? How much is the loss? That means it's 120 milliwatts minus 81.5 milliwatts. 120, this is 5, this is 8, this is 3. So this is around 38.5 milliwatts is being basically reflected by the load. So that is huge. And that's going back to the source. And that's going to create fluctuations, or I should say the ringing in the source. And it's sort of not desired, but it happens in the circuits. Okay. Now two lossy lines are to be joined end to end. You have two lossy lines. Let's say this is line 1, this is line 2. These are joined end to end. The first line is 12 meters long and has a loss rating of 0.30 decibel per meter. This is 12 meters long. Let's say this is 12 meters long, and it has a 0.30 decibel per meter loss rating. Decibel is just the unit of basically analyzing the power levels. That means if you have a line, you are comparing the power levels or at the 2 points. Let's say this is power 1, power 2. You can write the decibel reading as something like 10 log to the base 10 P1 divided by P2. Okay. There is one more thing called as decibel per milliwatt. This is basically represented as some power divided by some let's say 1 milliwatt reference power. This is a different unit altogether, and this is a different unit. These are two different units, by the way. And in decibel per milliwatt, this reference power basically depends upon what you are measuring. If you are measuring intensity, it's going to be different. If you are measuring power, the reference is going to be different. If you are measuring pressure, this reference is going to be different. If you are measuring, let's say, luminosity or optical flux, this is going to be totally different. So it depends upon the quantity basically you are measuring. And now what you are supposed to find, the second line is 10-meter long, and it has a loss rating of 0.20 decibel per meter, and the reflection coefficient at the junction is 0.30. That means the reflection coefficient here is basically 0.30. Determine the total loss in the combination. So we need to basically find the total loss. So first of all, we need to find the loss at the joint, which is basically this particular joint. So how can we find that particular loss is basically in terms of decibels, we can find that particular loss as, just like I told you, it's 10 log of 10 log to the base 10 of 1 divided by 1 minus gamma square, which is basically the reflection coefficient. Where does this come from? Where does this come from? It comes from here, because the transmitted to incident power is 1 minus gamma square. You have incident to transmitted will be 1 divided by 1 minus gamma square. So basically you're replacing two power levels by this 1 divided by 1 minus gamma square. As simple as that. Just like I told you here. The decibel is just the comparison between the two power levels. Okay. You have everything. When you put the value of gamma, which is this, you get a value of 0.41 decibel. And now the total loss in the line will be basically, in terms of decibels, it will be 0. This one 0.30 decibel per meter into how much was the length? 12 meters, because we need to convert it into decibel. So the meter will go, it will be in decibels, plus 0.41 dB plus 0.41 dB plus 0.2 dB per meter into the length of this, which is 10 meter. So this is the line 1, this is the joint, this is the line 2. So you add these, you compute the total, you get around 6.01 decibel as the loss. Okay, so the answer of this question is this particular thing. So whenever you are given two lines which are connected end to end, not this. This is, let's say, line 1, line 2, and you are given some loss of this, which is L1, some loss L2, and you are given what is basically the reflection coefficient at this particular point. You always need to find what is the loss here. Then you add this loss plus this loss plus this loss. That will be the total loss in the line. That's as simple as that. Because whenever you join the uh, two lines, there will be reflections at this particular line. Okay, because of those reflections, there will be losses in the voltage, and you need to compensate for those losses in the total calculation. Okay, so 100 ohm lossless transmission line, purely capacitive impedance. That means you have a capacitive impedance. Their R is equivalent to 0. The reflection coefficient of VSWR is, we need to find the voltage standing wave ratio. which is quite easy as seen in the previous this slides. This is Z naught. The ZL is already given. So you can find reflection coefficient as ZL minus Z naught divided by ZL plus Z naught. And you can find VSWR as 1 plus reflection coefficient divided by 1 minus reflection coefficient. So you compute this, you get this. When you compute the gamma, you get gamma to be zero point 0.6 minus zero point 0.8 J, and you compute VSWR, you get, uh, if you find the magnitude of gamma, first of all, it will be under root of zero point 0.6 square plus zero point 0.8 square. You get around 1. And if you put the 1 here, you get voltage standing wave ratio to be infinite. That's the case we have basically considered in the slides. So the reflection coefficient is 1. That means the entire wave is getting reflected. Nothing is going to the load. Nothing is going to the load. Okay. And all of the voltage which are being fed are being reflected back to the source. That's a terrible condition, basically. And you have this as mhm, this is oh, the options should be the V. Have I computed it correctly? Let me just see. If it is one, I don't know. This is one. Point
The
zero.
reflection coefficient is given. Yeah.
How much is it? No, the reflection coefficient we need to compute. Try to
Point
find me
0.6
some.
minus 0.8 J, that is given in the answer option. Yes.
Yeah, okay, sorry, sorry. Yeah, this is
Mhm.
given. Yeah, I was just confused. Thank you. Okay, so we have this as the answer of this question. I was just looking at the magnitude and I was like, okay, what's happening? So this is the magnitude. Okay, obviously. So this is the answer of this question, and I guess I am getting some sort of exhaustion now, and I'm not able to see the results. And that's why I will be finishing in maybe a couple of minutes because I have another meeting and then I will be ready to go. I'll solve up to question 5. And yeah, so another question now, this is question 4, which is basically uh, the question is that you have an ideal transmission line with the characteristic impedance. It's always most of the time 50 ohm. You are given the frequency, working frequency of 150 gigahertz. So it's saying that in order to avoid reflections, the line has been terminated by 50 ohm resistance. That means ZL is basically Z naught. So it's basically a perfectly matched what is called as transmission line. So the intrinsic impedance is 50 ohm. This is 50 ohm. However, the load unintentionally contains a series inductance as a result of which 50% of the incident power is reflected. Find the inductance. Okay, so this is quite I should say interesting because what it is saying is that you have a ZL, but this is complex. Why it is complex? Because it's saying that it has inductance, and when it has inductance or capacitance, there will be imaginary terms always associated with it. So it's some sort of x plus I times y, or rather, I should write it as z real plus iota times z imaginary. So we need to find what is that particular inductance associated with this. Okay, so it's sort of a resistance and inductance associated with the load. And because of this inductance, there is reflection. Uh, 50% of the power is reflected. That means 50% of the reflection means the gamma is zero point 0.5. That means the reflection coefficient is zero point 0.5 basically. And what is basically happening is that you have the ZL to be equivalent to, let's write it as RL, load resistance plus J times omega L. And you have R given as 50 plus J times omega L. L we need to find. And Z naught is already given as 50 ohms. Now you can find the gamma as ZL minus Z naught divided by ZL plus Z naught. I don't know what this means then. As a result of which 50% of the power, incident power is reflected. So let's try to compute this. You get gamma to be equivalent to ZL minus Z naught, which is basically J. Where is this? How much was? Okay, we are also given omega, by the way. Omega is 2 pi times frequency, so it's 2 pi times the 110 into 10 to the power 9 hertz. Okay, so you can basically write it as in terms of the in terms of this complex quantity which is given as it can be written as 50 plus j omega L minus 50 divided by 50 plus j omega L plus 50. This goes. This will be j omega L divided by 100 plus j omega L. This is gamma. Now, if you want to find, let's say, gamma magnitude square, you need to square this and you need to square this entirely, the numerator and the denominator. Now, what is basically given? You are given that the reflection coefficient is the magnitude of reflection coefficient is zero point 0.5. This is magnitude basically. So gamma is given as zero point 0.5. So what you can do is that you know that reflection coefficient magnitude is basically not exactly. You know that reflection coefficient magnitude square is reflected power divided by incident power. Okay, so what you will do is you will compute this is equivalent to 1 by 2 because the reflection coefficient is being given as 1 by 2, and basically this is not a way to do it. Let's do it here. If this quantity is given, that means we are given 1 over 2 is j omega L square divided by 100 plus j omega L square. And if you solve this particular thing, the only unknown is basically L, which is basically the inductance. Okay, so the question is 1 by 2 j omega L square divided by 100 plus j omega L square. Okay, we did a mistake. That is basically this j goes when we take the magnitude of it. So when we take the magnitude square, this j will go. So you are only left with omega L square divided by 100 plus omega L square. You open this, you solve this, put omega equals to 2 pi times frequency. You get the inductance to be equivalent to around 1.6 nanohenries. This is the exact answer of the question, which is basically this. But the note here that whenever you have to use the magnitude value, obviously the j imaginary term will not be there because you are computing the magnitude. That means basically you are squaring the both sides at this particular place. This j will naturally go, and you are supposed to compute the inductance that will be given by this particular value. Okay, I guess we are done for this particular session now. I have another meeting in just 5 minutes, and I have to run fast so that I don't miss that particular meeting. The answers to the other questions, which I have basically explained in the slides, I will upload them on the Google Sheet. Just go through them and go through the points I have basically mentioned in the slides during the initial part. I hope you will be basically able to solve these particular problems, which are not quite complex. So I hope to basically see you again in the next session so that we can continue solving these sort of problems and uh, have some fun with the electromagnetics. And I always try to basically, I should say, make it fun because otherwise, if you only go it by the Maxwell's equation and the mathematics of it, this subject might sound or it might look boring to the people who are basically studying it for the first time. And that's what happens most of the time. That's why if you see very few people are interested in microwave engineering or electromagnetics because once they encounter the differentials and the integrals and the Maxwell's equation, they think it as a sort of a they are afraid to solve it, which should not be the case because it's at the end the mathematics. But if you correlate it with different fields and your experiences and you are able to relate it with your day-to-day experiences, at the end of the day, these are just like all other waves you have been studying, except that these waves are associated with the electric and magnetic field, apart from the other waves. So that's why I try to just, I should say, include these things so that it becomes understanding and conceptually fun to learn these concepts. I should run because I'm getting late for the meeting. I'll be uploading this video on the YouTube and you can just check it from there, including the notes and the solutions to the questions. If you have any queries, you can directly reach me via the Google chat or you can just directly mail me. I hope I was able to clarify some of your queries or the concepts. See you again in the next week. Thank you.
Thank you so much.
Thank you. Have a nice day.
Same to you.
provide all the facilitation of student growth, সমস্ত facility পাওয়া যায়